String matching! The KMP algorithm. String matching is all about finding where little strings, or patterns, occur within big strings, or text. For example, let's try and find the pattern co in the text Coca-Cola. For small text like this, it's not too hard to spot where the pattern occurs, at position 1 and position 5 in the text. For a computer, finding where the pattern occurs wouldn't be too hard either. It could simply shift the pattern co along the text until there is a match. This is all well and good until the text gets larger, in which case the computer will have to make lots and lots of shifts to find a string match. This naive shifting algorithm has a complexity of O(n) times m and is not very good for string matching. The problem is we're having to make lots of shifts even when we know the pattern won't match. The Knuth-Morris-Pratt algorithm solves this problem by shifting the pattern by more than one position each time, and also pre-computes our pattern. The KMP algorithm consists of two stages, the prefix function and the actual string matching process itself. Let's start with the prefix function. The prefix function takes our pattern and finds matches of the prefix, or the beginning of the pattern, within the pattern itself. This may seem a little confusing, but hopefully this example should clear things up.
Okay, let's begin. To start, we set the variable length to the length of p. As we can see, this is 8, so length is 8. We then set the prefix of 1 to 0. And we set a to 0 as well. For b equals 2, up to length, which is 8, step 1, do, while a is greater than 0, which in this case it's not, so if p of 1 is equal to p of 2, which it's not, as p of 1 is a C and p of 2 is an O, so we skip to prefix b is set to a, which prefix of 2 is set to a, which is 0. And this is also still 0. We update b to 3, or a is greater than 0, which is not, if p of a plus 1, so p of 1 again, which is C, is equal to p of b, so p of 3, which is also C, this signals an overlap, as they're both C's, so a is set to a plus 1, which in this case is now 1. And the prefix of b, prefix of 3, is set to a, which is 1. b is set to 4, while a is greater than 0, which it is in this case, and p of a plus 1, so p of 2, which is O, does not equal p of 4, which is a, and O does not equal a, do a is set to the prefix of a, so a is set to the prefix of 1, which is 0. If p of 0 now, plus 1, so p of 1, which is C, equals p of 4, which is B, which it doesn't, so we move on to the final step of prefix b is set to a, so prefix of 4 is set to 0. b is updated to 5, while a is greater than 0, which it's not, so we can skip this. If p of a plus 1, so p of 1, which is C, is equal to p of b, or p of 5, which it is, as they're both C, this signals another overlap, so a is set to a plus 1, which makes it 1, and the prefix of b is set to a, which is now 1. b is updated to 6. While a is greater than 0, which it is, and p of a plus 1, so p of 2, which is O, does not equal p of 6, which is also O. Now these are equal, so we skip to if p of a plus 1, so p of 2, is equal to p of 6, which it is, then a is set to a plus 1, which makes it 2, and the prefix of 6 now is set to a, which is 2. This continues until we get to the end of the algorithm, at which point b is equal to 8, we return the prefix, and we end.
This part of the algorithm has complexity of O(n). Using this information in the second part of the algorithm will result in fewer shifts and faster string matching. Now time for the main event, finding where our pattern occurs in a long piece of text. Henry, take it away.
Here we start by setting n to 22, as that's the length of the text. We set m to 8, as that's the length of the prefix. We set I, which is the counter for the text, to 1. We set j, which is the counter for the pattern, to 1. And we set k, which marks the start of potential matches, to 1. While n minus k is greater than or equal to m, and this is true, so while j is smaller than or equal to m, and t of 1 is equal to p of 1, which it is, as they're both c, increase them both by 1. And again, because t of 2 is equal to p of 2, but here, t of 3 does not equal p of 3. So we break out of the while loop. J is smaller than m, so if the prefix of 3 minus 1, which is 2, is greater than 0, which it's not, so if I is equal to k, which it's not, k is set to I, making it 3. J is greater than 1, so j is set to the prefix of 3 minus 1, which is 2, which is 0, plus 1, making it 1. J is still smaller than m. We can compare t of 3 to p of 1, which we can see are different. So we skip down to here. If the prefix of 1 minus 1, so the prefix of 0, this doesn't exist, so we skip to here. If I is equal to k, which it is, as they're both 3, then I is increased by 1, making it 4, and k is set to I, making that 4. Now we compare t of 5, which is c, to p of 1, which is also c, which is a match. So we increase I and j by 1, and again, for we have another match, and this continues for the whole pattern until we get I is equal to 13 and j is equal to 9. At this point, j is no longer smaller than or equal to m, as m is 8, so we break out of the loop, and since j is greater than m, we output k, which is 5, and we can mark that there as well. Now, if the prefix of 9 minus 1, which is 8, is greater than 0, now this isn't true, and I does not equal k, so k is set to I. Doing this allows us to skip this whole string and start looking for another pattern match from this point. J is greater than 1, so we set j to the prefix of 8, which is 0, plus 1, making that 1. J is now smaller than m again, so we compare t of 13 to p of 1, which is again a match. So I and j increase by 1. We compare t of 14 to p of 2, which is also a match. So increase I and j. T of 15 matches p of 3, so again, increase them by 1. But t of 16 does not equal p of 4, so we break out of the loop. J is still smaller than m. So if the prefix of 3 is greater than 0, which it is, as it's 1, k is set to I minus the prefix of 3, which means k is set to 16 minus 1, making that 15. If j is greater than 1, which it is as it's 4, then j becomes the prefix of 3, which is 1, plus 1, making it 2. Now, we compare t of 16 to p of 2, and that's a match, so we increase I and j by 1. And again, for t of 17 matches p of 3. And this continues until I is equal to 23 and j is again equal to 9. At this point, we break out of the loop as j is greater than m, and since j is greater than m, we output k, which is 15. If the prefix of 9 minus 1 is greater than 0, and the prefix of 8 is 0, so we skip this, j is greater than 1, so j is set to the prefix of 8, which is 0, plus 1, making it 1. And k is set to I, making it 23. Now, n minus k is 22 minus 23, making that minus 1, which is no longer greater than or equal to m, so the whole algorithm ends. And we can see that the final matches start at 5 and 15.
This part of the algorithm has a complexity of OM. Therefore, the total complexity of the KMP algorithm is ON plus M, which is in linear time and far faster than our naive solution.